Like you can really see the left arm lifting.
University of Vermont professor Josh Bongard is no Dr. Frankenstein. For one, his lab contains computers instead of corpses. But Bongard does share with the fictional character an enthusiasm for creating life.
We try and borrow ideas from Mother Nature to build more agile, more capable, and more intelligent robots.
Though Bongard's lab may look like an unassuming place to be creating these new worlds, that is exactly what's happening.
We create a virtual world, and then inside that virtual world, we populate it with a bunch of virtual robots that are running around. So we have a population of robots. And then the computer reaches in and acts like Mother Nature, where the computer will cull or remove from the population those robots that aren't doing a very good job. The computer is in essence breeding smarter and more capable robots for us.
If it sounds kind of complicated, that's because it is. Bongard's research is a combination of science and technology, borrowing ideas from engineering, biology, physics, and neuroscience, just to name a few, to create the computer-generated worlds inhabited by robots.
Evolution is a fantastically complex process. It's been going on for billions of years. And so our challenge is to try and understand what parts of biological evolution should we try and copy in our computer programs.
Over time and subsequent generations, Bongard's virtual robots evolve in form and function to suit their environments. Or not. It's a new field, and evolution can be unpredictable.
We're often surprised by the results of our computational evolution. Sometimes the surprise adds to our blooper reels, where the robots do something that they'd never be able to do in reality, jumping 100 feet in the air or disappearing through the floor.
Besides the intense combination of multiple disciplines, the research also requires complex math and an abundance of patience.
It's not just a matter of playing with robots in a simulation, it's creating this world that runs according to its own rules. And if those rules are correct, we get what we ultimately want, which is a useful, complex robot.
Even the name of the lab is fairly intense. Just ask one of the PhD candidates that works there.
My name is Shane Silas. I'm a PhD student in Josh Bongard's Morphology, Evolution, and Computation and Cognition lab.
Silas's work focuses on making the research accessible to ordinary people and developing ways for anyone interested to interact with the robots themselves.
What I want to be able to do is to be able to have people download an application, maybe look at a YouTube tutorial, and be able to essentially kind of draw out some robot shapes.
Getting more people interested will help get more research done faster.
We're trying to create web-based tools where users or students can go online and interact with these virtual robots or evolve robots on their own. And so the benefit for the user is its educational or its entertainment value. But while a whole number of users are creating a large number of robots, they're generating useful research results for us.
But it'll be interesting to see on the environment pairs if there are different subsets.
Josh Auerbach is another PhD student in Bongard's lab.
An object that small.
And so, for instance, we can evolve a robot that'll move really well on this ground. But if we put this same robot in one of these icy environments, it just thrashes around and doesn't move at all and kind of just looks like a fish out of water almost, or something like that. But if we evolve a robot in this environment, it can be uniquely adapted to it and be very successful.
Auerbach's research looks at the mechanics of evolution and how different environments affect the way the robots evolve.
They can take on any arbitrary shape, and evolution can try all these many different things. Whatever works succeeds, and that's what the end products will be, as opposed to coming in with a preconceived notion that an engineer has that we should have legs and sensors in specific locations and built in a very specific way that's informed by a lot of their biases. And we think that by kind of taking this step back and giving evolution this freedom to tinker with all these different shapes and different ways of combining these shapes and actuating these shapes, that we can create more successful robots in the long term than we will be able to do by relying on our intuition.
The long-term goal of this research is to create successful robots in the virtual world that could translate to the physical world.
If we do succeed at creating virtual robots, how do we transfer that into a physical robot that can do something useful in the real world? And this is known in our field as the reality gap problem. You have to jump over the gap from these virtual worlds to the physical worlds. So part of the research is, can we get our computer programs to design in these virtual robots a robot that works but also has the potential of crossing the reality gap, that the computer would tell us how to go about building a physical version of this virtual robot.
But it does look
And
like it
that
uses
would make
just one
Bongard
part of the
very
body
happy.
to always
I was
go
always
into
interested in robots, and you see robots in the movies, they usually play the bad guys, but you don't see robots in our everyday lives. And so when I was quite young, I wondered, where are all the robots? Why don't we have them yet?
There is quite a long way to go before we start seeing robots in our everyday lives. But the research coming out of Josh Bongard's lab at UVM is leading the way. In Burlington, I'm Rebecca Gollin with Across the Fence.